Hi everybody, this is the second part of the lecture on section 4.7. So last time we left off with an example of an applied maximum minimum problem. Let's do another example. So consider the following two lines. Line 1 is got these parametric equations, 1 plus t, 1 minus t, 1, and line 2, and let's use a different parameter here. We'll use s. 1 plus 2s minus s, 1 minus s. Okay, these lines are neither parallel nor intersecting. Find the 2 points on each line. Well, find a point on line 1 that's closest. Find the points on line 1 and line 2 that are closest. Find the shortest distance between a point on line 1 and a point on line 2. And also, what are those points? Okay, so just a visual aid here, right? We've got, these two lines. They're not parallel and they don't intersect. And, we're looking for somewhere where these two lines have the shortest distance between them. All right? So, well, the distance between two lines, between, a point on this line and a point on that line, is given by the distance formula. So the distance is equal to 1 plus t minus 1 plus 2s squared. So I need to move this. So that's the difference in the x-coordinates, plus the difference in the y-coordinates, 1 minus t plus s squared, plus the difference in the z-coordinates, 1 minus 1 minus s squared. Okay, and if we're trying to minimize d, we might as well minimize fst, so here we have a two-variable function, equal to the distance squared. And that is 1 plus t minus 1 minus 2s. So that's t minus 2s squared. So no square root, it'll be easier to calculate derivatives. Plus 1 minus t plus s squared plus s squared. So here's our two-variable function. And, in this one we don't have to reduce the number of variables. We already have just a two-variable function that we're trying to minimize. And, we use this trick that was used in Calc 1 as well. When you're trying to minimize the distance between 2 points in 3 dimensions, 2 dimensions, whatever, the distance function has this square root. But minimizing a square root, you might as well minimize what's under the square root, because the square root is an increasing function. All right, so this is the function that we're looking at. So certainly we're going to have to do some simplifications here. But before we do those simplifications, we can just start taking derivatives. Right? There's no need to do the simplification before the derivatives. Okay, so we're looking for the critical points. So the derivative of f with respect to s is equal to 2t minus 2s times minus 2 plus 2 times 1 minus t plus s times 1 plus 2s. Right, so no need to evaluate squares there. So this is minus, it's 2t minus, no, sorry, minus 4t plus 8s, right? So that's 2t minus 4s, so that's minus 4t plus 8s, plus 2 minus 2t plus 2s plus 2s. So this is equal to, I have minus 4t minus 2t, so I have minus 6t plus 8 plus 10 plus 12 plus 2 equals 0. Right? The critical points are where both partial derivatives are going to be equal to 0. So that's the first partial derivative that we need to look at. The next partial derivative, f with respect to t, so 2t minus 2s times 1 plus 2 times 1 minus t plus s times minus 1, and then plus 0. So this is 2t minus 2t right, 2t minus 2t. What happened here? Plus 2t. 2t minus minus plus 2t. So that's 4t. And then I have minus 4s minus 2s. So that's minus 6s plus 2 or minus 2. And that's equal to 0. So we have two linear equations with two unknowns. 4t minus 6s equals 0, and minus 6t plus 12s equals, not 0, I'm sorry, 2, and 2, minus 2. Right, these are the two equations that we're working with, and you can solve that in whatever ways you want. I would multiply the top equation by 2 and add them. So I have 8t minus 6t is 2t, minus 12s plus 12s is 0, equals 4 minus 2 is 2, so t equals 1. And when t is equal to 1, what do we get here? Minus 6 plus 6 of 12t 12s is equal to, so 4, so s is equal to 1/3. So that's the only critical point. 1/3, 1 is the only critical point. So this is where the minimum must occur. Okay, So in all the problems that we're going to be working on, I'm going to give you problems where you only get one critical point in these applied problems. So the question of whether the maximum is there or here or somewhere else, that question will be avoided. We'll just, have one critical point, and therefore that's where the minimum's got to be. So on line 1, where x is equal to 1 plus t, y is equal to 1 minus t, z is equal to 1, we get the point 2, 0, 1. And on line 2, where we had x equals 1 plus 2s, y is equal to minus s, and z is equal to 1 minus s, at 1/3, we have the point 1 plus 2/3 is 5/3, and then minus 1/3, and then 1 minus 1/3 is 2/3. So these are the 2 points that are closest together. And the distance itself so 2 minus 5/3, that's 1/3, squared, plus 0 minus minus 1/3 squared, plus 1 minus 2/3, how about that, 1/3 squared. So the distance here is square root 3/9. So root 3 over 3 is the distance. So that's the shortest distance between 2 points, one point on the line and point on line 2. Okay. So that's a couple applied problems. We'll work on some more during the discussion. The final topic in section 4.7 is definitely related to this. Max, min values, so absolute max and min values. For continuous function. On a bounded domain. And the basic fact here is the following. Given z equal to fxy on some domain R, some finite measure domain, finite area bounded on some bounded domain, we'll say. So bounded domain R consists of a couple things. You've got the interior of R, and then you've also got this boundary of R. So as long as fxy is continuous, okay, the absolute max and min for fxy on R occur either at critical points or on the boundary. Okay, they occur at critical points or on the boundary. And on the boundary, fxy will reduce to a single variable function in some way. So you'll see that in just a little while here. So we're going to find the critical points in the interior of R, the two variable critical points where the partial derivatives are equal to 0. And then on the boundary, f will turn into a single variable function, and we'll use the technique learned from the max-min section in Calc 1. And we'll calculate critical values of the single variable function on the boundary, and then, find the max value on the boundary, min value on the boundary, and in the interiors as well. And then you just compare them, say, oh, this is the biggest and that's the smallest. So, for example, so find the absolute min and absolute max values of fxy equal to x to the third minus 3x minus y to the third plus 12y on r equal to this. So the square here, where this is 0, 0, 1, 0, 0, 1, or no, 0, 0, 3, 3, 0, 3, 3. So we've got this square here, and we want to find the absolute max and absolute min values on this region here. Okay? So first thing, we'll find the critical points of the two variable function. So take the partial derivative with respect to x, 3x squared minus 3, and these are just 0. And then fy is minus 3y squared plus 12. So here, this gives us x equal to plus or minus 1. This gives me y equal to plus or minus 2. Okay, so where is the critical point? Well, in this one here, the x and y coordinates are all positive. So I can't use the negative ones. So this is like positive 1, 2 right here. Right, and that's our only critical point. There's also negative 1, positive 2, negative 1, negative 2, positive 1, negative 2, but those are not in R. The only such point in R is 1, 2. So that's our only critical point. So now stick that into the function. See what the value is. So we have 1 minus 3 minus 8 plus 24 is equal to, so it's 25 minus 11, 14. So the value of the function f at that critical point is 14. Now we need to look at f on the boundary. Okay, the boundary consists of 4 separate sides. All right, so now let's look at the boundary. So the boundary on the bottom here, these are the points x0 for x between 0 and 3. Zero, zero, 3, 0. So the point here, x0 minus 3 less than or equal to x less than or equal to 3. So boundary component 1. So boundary component 1 is this. All the points x0, where x is between not negative 3 and 3, 0 and 3. All right, go back to the function. The function is right here. All right, that's f of xy. Now put in x0. So f of x0 is just x to the third minus 3x. Right, so that's a single variable function. So now f prime of x is 3x squared minus 3. So the critical point, set that equal to 0, the critical point in the single variable sense is x equal to plus 1 and minus 1. Right, of course this one is not in the domain for x between 0 and 3. So x equal to 1 is the critical point. And then you also have to check boundary components, or the boundary points as well, remember? So for the single variable function, you check the value of your function at the critical point and also at the endpoints, the boundary points. In one-dimensional regions is just 2 points, but in these higher dimensional regions, you get more intricate things. So just plug in those values. F of 0 is minus 3. F of 3 is 27 minus 3 is 24. And f of 1 is 1 minus 3 is minus 2. All right, so we've got these values here on the first part of the boundary. So far, we have max value 24, min value negative 3. Boundary component 2. So similar to that is the top side of that rectangle. So this is the point 0, 3, 3, 3. So these are the points x3, where 0 is less than or equal to x, less than or equal to 3. And the function fxy becomes fx3. So that's x to the third minus 3x, and then at 3, this is minus 27 plus 36, so plus 9. All right, so the derivative of this single variable function, f of x, is 3x squared minus 3. So again, x is equal to plus or minus 1. But of course, minus 1 doesn't count because it's not in the range for x, or domain for x. So now checking the value of that function at that point, f of 1, you have 1 minus 3 plus 9, which is minus 2 plus 9 is 7. Boundary component 3, so these are the points 0, y, 0 less than or equal to y less than or equal to 3. So the original function is that. So f of 0, 3 is just minus y to the third plus 12y. I'm sorry, 0y. So f prime of y is minus 3y squared plus 12. So this gives me y equal to plus or minus 2. Right? Of course, we can't use the minus 2 because that's not in our domain for y. Y should be between 0 and 3. So negative 2 is not used there. So now just checking out this function at the point positive 2, what do we get? We get minus 8 plus 24, 16. And then boundary component 4 is the line 3, 0 to 3, 3. So this is the point, not 0y, 3y for 0 less than or equal to y less than or equal to 3. Again, the function is this. So on this part of the boundary, you have f of 3y is equal to, so this is 27 minus 9. 27 minus 9 is 18 minus y to the third plus 12y. So now the derivative of that, f prime of y, is minus 3y squared plus 12. So again, y is equal to plus or minus 2. Well, minus 2 or plus 2. Right, the minus 2 doesn't count, so now we just have to check. Just check the critical point. So f of 2 is equal to 18 minus 8 plus 24. So that is 34. 42 minus 8 is 34. By the way, you don't have to check the boundary points anymore. I checked the boundary points 0, 3 and 3, 3 here. Or no, I didn't. I'm sorry. F of 0, 3 and f of 3, 3. So we have to check f of 0 here. F of 0 is 9, and then f of 3 is 27 minus 9 plus 9, 27. So we've checked all 4 of those corners. We checked the corner 0, 0, 3, 0, 0, 3, 3, 3. So on this one here, there's no need to check them again because the values don't change. So what's our max value? Well, our min value here is negative 3. And our max value, I guess, is 24? No, 27. Max value 27. No, 34. All right, so absolute min minus 3 for f of x and absolute max is fxy equal to 34. And that's it. All right, so you find the critical points in the interior of the region and then see what the value of f at those critical points are. And then you find the critical points on the boundary, and the function becomes a single variable function on the boundary. So check the derivative of the single variable function on the boundary, find the critical points of that, test their values along with the endpoints of the interval, and then just compare all the values we have, right? I mean, we have here 34, and then 16, and 27, 7, And then all these numbers here, 24, negative 3, 14. So the largest number was 34, the smallest number was negative 3. Okay, so that is the end of the lecture on this section.